Hi everyone, today I'm gonna do a presentation on the emergence of a novel domain expert, a generative AI-based framework for software function point analysis. Accurately estimating software function size before development is crucial in requirements engineering, as it determines software cost and project timeline, ensuring smooth project execution. Function point analysis is employed to assess function size by analyzing the software requirement specification. Among various FPA methods, the International Function Point User Group has adopted the widely utilized high-level FPA approach. Despite the existence of the standard FPA method, manual analysis remains challenging, suffering from the disparate experience and capability of individual analysts. On the one hand, manual analysis requires understanding detailed definition of software function points. On the other hand, the manual analysis workload in practical application is immense. The SRS needs to be divided into requirement projects for each subsystems, with multiple FPA analysts applying the FPA method to their respective subsystems, generating corresponding FP entries. And finally, complex cross-validation is required to eliminate personal errors, which consume significant human resources. Accordingly, to reduce costs and to enhance efficacy, there is an urgent need to leverage AI-based techniques to accomplish FPA tasks. So here, let's dive into our pipeline of the FPA-EX framework. For the first time, we constructed a multi-domain FPA dataset consisting of 778 QA pairs mapping to 1744 FP entries, which serves as a foundation for subsequent fine-tuning and evaluation. Secondly, to intelligently extract software FP entries directly from SRS, we proposed a novel generative AI-based framework employing large language model named FPAEX, which subvert the original manual mode. Thirdly, considering precious FP's extraction, we present a densely supervised fine-tuning of large language model and concept act prompting for inference, realizing efficient learning of FPA knowledge. Finally, FPAEX achieves the state-of-art result compared with other advanced models. In terms of practical application assessment, FPAEX significantly reduces work cost and increases production capacity. So dive into the method. The first part is to establish a FPA dataset suitable for fine-tuning generative large language models. We initially collected approximately 15 SRS, each spanning around 300 pages from various domains such as Office Software SRS, Social Media SRS, and System SRS through collaborations with companies. These SRS are annotated by professional FPA analysts working at this company, identifying the corresponding FP details in SRS paragraphs, which include 5 categories: ILF, EIF, EI, EO, and EQ. And then we started fine-tuning the pre-trained generative large language model decoder using a low-rank adapter on the dataset created in the first stage, a well-established method in large language model fine-tuning. We selected Q172b as our base model to ensure fundamental generative capability. We then derived the corresponding output tokens via tokenizer and transformer blocks in decoder. And finally, we computed the cross-entropy loss with the tokenization of ground truth answers. However, a notable long-tail issue arose in the FP extraction within SRS. Some categories suffer from insufficient FP samples, challenging conventional large language model fine-tuning approaches and leading to significant extraction missings. Our DSFT achieves more fine-grained entry-level optimization through entry-by-entry adjustments, which can focus on learning difficult content generations. And to ensure correct logic, reasoning, and precious extraction of reasonable and complete FPs in complex scenarios, we developed a concept-act prompting method. Different from other prompt engineer methods such as simple in-text learning or chain of thoughts that overemphasize the reasons of process, our concept-act prompting activates critical information by introducing special contents, which increase the accuracy of our result. So in this page, we have a table to visualize the results when comparing our FPA model with other large language model. So we evaluate the performance of FPA-EX against other algorithms on the same test set. Both quantitative result and visualization demonstrated that FPA-EX significantly outperformed the alternatives. And apart from that, in practical applications, FPA-EX is indispensable as it significantly simplifies analysts' work by enhancing efficiency of FPA and leading to a substantial increase in productivity. Thanks for listening, and we welcome collaboration on work and researching related to software size estimation and software function point analysis. To contact us, please reach out to Mr. Ren Zhao.